This case study looks at a small ship, small fishing boat, the given mass that's being towed by a larger tugboat. There's a tow cable here that we're going to assume can be modeled as a linear elastic element, spring, so we can estimate, given how much it elongates for a given tension, and that I hope you identify can give you the stiffness, right? Since you can say, okay, C is approximately the change in the force that you put on it over how much it changes, right? That's your basic definition of stiffness. As the boat's being pulled through water, it has some viscous drag, and we're going to assume that we're given a reasonably good estimate of damping on that, and we'll model it linearly. Could always change this and look at nonlinear type damping, which is probably more realistic, given that this is a flow around a bluff body and a fluid. And that's one of the nice things about building a simulation the way we'll do, is that we can always begin with some linear approximations. Since we're using a simulation, we're not restricted to the linear constitutive behavior that we might have for certain model elements, and we can change the constitutive behavior to be more realistic if it requires some kind of nonlinear behavior. Let's assume that at time zero the tugboat starts pulling here with some specified constant velocity. So we're going to say that this v of t is actually going to be almost like a step for all intents and purposes, and we'll look at that. Nothing is a true step, right? But it's eventually going to be going at 5 feet per second. And build a simulation to determine, how fast the tugboat's going, which is given, but also how fast eventually the boat will go in the transient period, and then at steady state. We want to see how the distance that the boat's going to travel, how much the cable extends, the cable extension, and then also individually look at the cable force and the drag force. So the cable force will be the elastic force, and then plot these. Okay, so this is a nice little simulation case study. More appropriate here might be that we're modeling this essentially as a mass spring with a velocity input here and some linear type damping here, right? So we want to know how fast is this guy going. So relatively simple system. We have the weight of the boat, damping. I'll note that these are English units. I highly recommend that you convert to SI units. Much more consistent. The original problem that I derived this from was all given in English units, but convert to SI, much more consistent. Thinking of the problem in this way, and this is linear spring force here, we want to know the extension of this cable, so we have a state equation for that, which is v of t minus, and this term here is just Vm. I expect as I'm going through here, you will for yourself derive these equations that are using basic Kirchhoff type approaches, right? The velocity of the boat comes from Newton's law on a free body diagram for this mass, which would be P dot m, right, with the sum of the forces on here, which we'd eventually write as, say, m, v dot m, and that's where that equation comes from. So v dot m is the spring force minus the damping force, this is v sub d, divided by m. We're going to want to add two additional states here. Remember, information states. One of them is we want to get the position of this mass, so that simply comes from that the rate of change of the position is just the velocity of the mass, and the position of the tugboat, right, is just Vt, right, and these are the same in my notation. So now we have the state equations. We want to build a simple simulation for this using some of the methods that we've been talking about. Okay, what I have here is a system function file, and it extends here. It's a little bit longer. And note the first line being the definition of the towed ship problem. It's got the time and the state vector here. Also note that I'm going to be using the format where I'm going to have output variables also being computed, and I'm going to show you how those can be used. As I've mentioned, you may want to put a comma in here. It'll still work this way, but Matlab may tell you that it prefers that you put a comma here in these row type vectors. The global definition is required here because there's some parameters that I define in the system, in the simulation file. And going through here, I'm defining using physical variables the states that come in here, right? So this is size n equals 4. So I have 4 states, and they're all here: the extension of the cable, the velocity of the towed ship, the position of the towed ship, and the position of the tugboat, just as I've just defined. But I put them into these physical variables so that I can more easily write my relationships here. Now, starting off with the input, I have a conditional here. I defined a time that I want the tugboat to start pulling, and I say if t is greater than or equal to t on, then the tugboat velocity is the value that I define. Otherwise, it's not moving yet. Okay, so I wanted to show you here one way that you can include command or input type commands, as using basic conditional statements within the function file, right? Because you want this to happen, as it's being simulated and solved by the equations. Okay, you could also look at defining, this basically is saying that at t on, this thing's going to just jump up to v naught. An alternative is to have the input defined by a hyperbolic tangent that turns on somewhere around here. So this is a hyperbolic tangent, which is a nice smoother function for the velocity than a step. This would more properly model the tugboat engagement and wouldn't give you such sharp inputs, which again are not realistic necessarily. The function continues up here, and the other conditional I have here is there's actually a nonlinearity in the spring element, right? Even though we modeled the cable as a basic spring, right, we're going to say that it does, if you, we're going to say that if you have it in tension, then the force engages and you have this nice linear, extension. But if you try to loosen it too much, right, if you don't have any tension, if you try to compress it, the force goes to 0, right? So actually that's what this says here, that if you're in tension, you get a linear force, but if it goes slack, so when the cable goes slack, there's no force being transmitted, right? So basically, your boat has no force on there because you've pushed it negative, right? So it's only when it goes into tension. Finally, here's the definition of the forces. So you see how I've defined FC and FB within the computations. See, that allows you then down here in output variables to send them out, and you can then later call these not only the forces but also the specific velocity input, because these are not states, these are not variables that will be available through the solver. So I'll show you how you call these up later. Okay, so note they come after your definition of the state equation. So here now the state equations defined exactly the way we derive them. X dot 1 is the extension of the cable. It's the difference between the velocities. Here's V dot M, the sum of the forces, and then finally the two motion variables. Now let's look at the file that is being used to simulate the system. There's a lot going on here, but what I want you to focus on is a few of these things. This is all the plotting here, so you can study this later, and I may provide this example as a download. Let's focus in here on the first part of this. This side here sets up the simulation and calls RK4 fixed, so you can see here. After it's solved, then the output and processing. So first, let's look at this side here. Remember, I do clear all here in case I'd run any other simulations. I want to clear all the variables, and I want to define all my globals. All my parameters are being set up here. So really, all of this here is just setting up parameter data. So you can see there's not a whole lot to running the simulation. A lot of it is in the system function file, which we just reviewed. Setting up the initial conditions. I'm starting at 0 position, 0 velocity, 0 position of the mass, and for the tugboat. Right? Sorry, this first one here is for these. We're assuming that the cable starts just slack. There's no force in it. Okay, so like if we draw it again, we're at this point here. So there's no force. It's also not slack, but it's at 0 force. You could start at pre-tension, but then it would be moving. Okay, so we start off at 0. Now I build my initial condition vector. Okay, then I'm going to integrate for 5 seconds with a step of 0.01, so I compute my number of steps. We've gone through all this before in those simpler examples. I have this one commented out where I called ODE 4.5, but I'm using RK4 fixed. Different notation here. It used to be you could put quotes around this. I should put the newer notation here where it's called, the file is denoted by the @ symbol, toad ship. Either one works in RK4 fixed. In ODE 4.5, it expects you to use this @ symbol. There's your initial condition vector and number of time steps. Okay, now the one step that's new and different from some of the simpler examples we went through before. You recall that in the system function file, I defined some output variables. And the output variables that I wanted to know about from the simulation were they're listed here. They're the velocity of the step, cable force, and the damping force. So the way and this is the key step right here, you can use that function file, the sim function file, in any calls this way. So what I'm doing is I'm going to step through all the time steps. I've already computed, right? I already have t and x. And remember, x has all the states over all those times. So I send those values step by step. And that's what this does here for I equals 1 to n, because there's n steps in time. And in the y vector, I read it. So I go back into toad ship. I send it the time and the actual states. And remember, it'll compute those velocities and forces again. Anything that you put in this y vector, it sends them right back in the y, and then you can define so that you can plot down here together with everything else these dynamic variables that are functions of state. This is, I think, a very helpful step in outputting variables that can help you gain more insight into what your system's doing, and I'll use it in most of the examples that I'll show you. So now once you have those variables, you can specify your plotting. I like to use a subplot, so I get one single plot, right, with here's this, I can define a number of plots, a 3 by 1, and I put all 3 plots together over time. So I'm plotting velocities, distances, and forces. Let's look at what the results look like for this simple example. So I've got the velocities, distances, and forces here. The first one here shows the tug velocity, which is constant, and then the boat velocity, you can see the boat is accelerating and reaching finally a steady velocity. And here's the tug travel, and the boat travel lags right behind it. So at the end of the, once it reaches kind of a steady state, there's always a little bit of a gap there, and that's actually equivalent to how much of the cable extends. If you look at it, that's about 2 meters there, right? And then here finally are the cable and drag forces. Note at the very end, the cable force balances the drag force, so you're just barely having to keep this, give it enough force to keep it going. You're just overcoming drag. This difference here is due to, because you're accelerating, so there's some inertial force that you're having to overcome, but once you overcome that, it steadies out. Okay, so it all makes sense. This is what we call this is what we call verification. It's doing exactly what you want. Now you could go in and play with the model, change parameters, introduce other effects, and so on.